Good morning, everyone. My topic today is numerical simulation of the open-hole oscillating flow type wave energy converter based on OpenFOAM. My talk will be in 4 parts: research background, research method, research content, summary, and outlook. First, let me introduce the oscillating flow type energy generator. It converts wave energy into mechanical energy through the float connected to the generator, and then converts the mechanical energy into electrical energy through the generator. It is low in cost, easy to build, and has high power generation efficiency. It can better adapt to sea areas with lower wave energy density, which is consistent with China's wave conditions. Oscillating floats can be divided into fixed and floating types with the same working principle. To improve the system energy efficiency, the current research focuses on the optimization of structure design and multi-degree of freedom research. And in order to solve the hydrodynamic performance calculation of the wave energy utilization diverse. A numerical water tank which can obtain detailed flow field information and low cost is selected. And the governing equation are the continuity equation and the Navier-Stokes equation. And discretization of the governing equations using the finite Warren method. For incompressible fluid, we choose the K-epsilon turbulent model, and we check the free liquid surface by the VOF method. We used OpenFOAM V1912 and Waves2Foam for simulation. Then combined WaveFOAM and over interdynamic mesh foam to get solver over wave dynamic mesh foam. About mesh, we used both overset mesh and dynamic mesh. The size of the numerical waveform model is 80 meters long, 10 meters wide, and 17 meters high. And this is the size of the numerical waveform model. The wave depth is 10 meters. We got relaxation zones at both the inlet and the outlet. The background grid size has an aspect ratio from 1 to 4, and the grid in the free surface area is refined. We designed 3 sets of the grids and compared with theoretical value, which calculated by the wave surface equation. And the grid 1 with a small number of grids and a high fit between the calculated value and the theoretical value was selected. And this is the numerical simulation of the waveform. And this is our float models. One without a hole, one has 4 holes with a diameter of 400 millimeters. When generating the mesh, we took 2 approaches. First of all, the STL field of the model is imported into OpenFOAM, and the mesh is generated with its own SnappyHex mesh tool. Another method used pointwise software to generate mesh and import OpenFOAM, and finally selected the mesh generate used by pointwise. And this picture shows the numerical simulation of the float motion. These are the conditions we choose. At different wave height and different wave period, it shows different status. In this table, we can see the heave amplitude is closely linked to the wave height, exhibiting minimal correlation with the wave period. When reaching a wave height of 2.5 meters, the float entered a critical state in which they were overturned and suffered damage. It means the floats are unable to supply electrical energy to power generation device. So a single float with no openings is limited to a maximum wave height around 2.5 meters. When comparing the average heave amplitude to the float with 400 mm holes in different working conditions, we can see that the average heave amplitude of the floats was mainly affected by the wave height, whereas the influence of the wave period was relatively small. And we can come to the following conclusion. The average heave amplitude directly reflects the capture ability of wave energy. For floats with different shapes in the same wave height, the amplitude is less affected by the wavelength. The adaptability of the float works with open hole to different working conditions is obviously better than that of the float without open hole. Its application effectively solves the problem that the solid float will turn over under large Z conditions. In the future simulation study, we can try to simulate float movement under different wave type. The above studies only simulate the case of Stokes' first wave. Or we can explore other float shapes, changing the number and shape of the openings, and choose other opening forms, such as placing the openings on the side walls of the float. And we can also simulate float motion under different array combinations. And that's all for my presentation. Thank you.